Our next speaker is John Lindy from University of Washington, and he will tell us about how to use P4 in a very novel way.
All right, thank you for the introduction. Good morning. So I'm John Lindy from University of Washington. Today I'm very excited to tell you guys about how we have this very innovative use of programmable switches to improve load balancing of distributed storage systems. So this work is in collaboration with a bunch of folks, including Alice Michael, also from University of Washington, and Jacob Nelson and Dan Ports from Microsoft Research, as well as Xinjin from Johns Hopkins University. I think both Jacob and Dan are here today, so if you guys have questions, feel free to talk to us after the talk. All right. So as you all know, tweets from a celebrity like Justin Bieber receive millions of requests, retweets, and comments. However, if you look at a tweet from me, it basically gets zero traffic. So this phenomenon is actually very common in real life, and we even have a name for it called the power law. It says that a small fraction of popular requests actually accounts for majority of the traffic. At the same time, the set of popular items change rapidly as new trends rise and fall. So these highly skewed workloads imposes a lot of challenges to distributed storage systems. So for these systems, they typically partition their data across multiple storage nodes. So the server that unfortunately stores the popular tweets from Justin Bieber will receive way more traffic than some of the other servers, and will quickly become overloaded, as indicated by this load bar. So this load imbalance can significantly impact system performance, as requests going to these overloaded servers will suffer much higher latency, and it will limit the overall system throughput. Well, the next time you see this page on Twitter, you should know who is causing it. Okay, so to deal with this problem, there are some previous approaches, for example, using caching. So if we can build a faster caching layer, and we cache some of these popular items in the cache, then requests to these popular items can then be absorbed by the faster caching servers. And this approach will help reduce the load on the backend storage system and make the load across them more uniform. However, there are several limitations of this caching approach. First, it has shown that the caching layer needs to be orders of magnitude faster than the storage layer for this approach to be effective. But actually building a magnitude faster caching layer is becoming more and more challenging as the storage systems themselves are becoming faster and faster. So there have been proposals actually using programmable switches as a caching layer, but that approach also have several limitations, like there's limited space on the switch, and so limit the key and value size of your requests. And second, a fundamental limitation of a caching approach is that it is only effective for read-heavy workloads, because writes still need to be processed by the backend storage system, and it incurs additional cache invalidation traffic. So in our approach, we build a system called Pegasus. So we take a different approach. So instead of caching, we selectively replicate popular items across multiple storage servers for load balancing. And then, in order to maintain the set of replicated objects and also the location of the where the servers have the latest copy of the data, we build the innovative in-network coherence directories directly inside the switch data plane. By this innovative co-design approach, the Pegasus is able to provide provable load balancing for both read-heavy, write-heavy, and rewrite mixed workloads. So selective replication conceptually is actually very simple. So it replicates popular items like Bieber's tweet on multiple storage servers. Then requests for these objects can go to any of these servers, effectively balancing load across the backend. So, but there is a question of how many objects should we actually replicate. So by replicating more objects, it gives us more opportunities to balance load. But over-replication will significantly increase storage overhead. So on the other hand, if we do not replicate enough objects, then we won't have enough load balancing benefit from this approach. So the interesting observation we have in this work is that we only need to replicate the most popular n-log n objects, where n is the number of storage servers, for us to have very good load balancing properties. And after that, we can forward this request to these replicated objects to the server with the least loaded server. And we prove in our work that it can give us a very good load balancing with high probabilities. So I have to note that this is a generalization of a previous result based on caching approach. Okay. So far I talked about how we use selective replication to give us good load balancing. But there are actually a lot of challenges in actually realizing it. So first, how do we keep track of the most popular n-log n objects in the system? As object popularity changes constantly. And second, how do we manage all these replicated objects? How do we find the location of the servers that has the latest copy of these replicated objects? And also, how do we actually locate servers with the least minimum load when we do this load-aware forwarding? And last, how do we ensure a strong consistency when there are concurrent read and write requests, especially to these replicated objects? Well, to solve these challenges, we propose an innovative use of these programmable switches by building an in-network coherence directory. So what is a coherence directory? So I hope for the computer architects in the audience, it should be a pretty familiar concept. So coherence directories are commonly used in multiprocessor architectures and distributed shared memory systems. So essentially, they track, for each cache block, they track the state of the block as well as the set of processors that currently have a shared copy or exclusive copy of the cache block. And they work with processor caches to coordinate coherence protocols. So how do we use a structure, a coherence directory-like structure, to help with selective replication? So in this directory, we can keep track of the identity of the objects, the most popular objects in the system. And for each of these popular objects, then we can track the set of servers currently have the latest copy of the data. So all the storage requests will go through the coherence directory first. So the directory will check if the request is for one of these popular replicated objects. If there is a match, it will pick one of the servers from the replica set, essentially the server with the least minimum load, to send the request to. So one important contribution of our work is to demonstrate that we can build this coherence directory efficiently on programmable switches. And just to briefly give you a high-level sense of how we actually build that in a Tofino-like switch. So we use multiple pipeline stages. Essentially, in the first pipeline stage, we match the object ID, the hash of the object key, in a lookup table. And the action is actually an index that we can use in later stages. And then we use multiple register arrays to store the replica set. And we use the index from the previous stage to identify which index to use inside these register arrays to find the replicas for that particular object. And then after we identify which server has the minimum load, which I'll briefly talk about later how we do that. And the next stage, we do build a forwarding table that match on the destination server ID and rewrite the destination address so that we can forward to the server we selected. So due to time constraint, I won't go into details of many of the technical challenges and how we solve them. But here I give a brief overview. So first question is, how do we actually track which server has the minimum load? So that problem has two parts. So first, we need to know the load of each server. So for that, we have multiple mechanisms, including a reverse in-network telemetry, where the server will include the load metrics in their reply packets coming back to the switch. But there is a slight problem with that approach. Is called a control loop delay, where when the switch receives the load from the reply packets, it's already a little bit too late when they make forwarding decisions. So we decided another approach where the switch will predict what's the current load on each server by tracking the current outstanding number of requests it has sent it to each server. And how do we actually track the most popular unlogged objects? For that, we build a statistic engine on the switch to track the access rate of these replicated objects. And the controller will pull these access rates and compare them to a hotkey reports from the servers to determine what's the current most popular unlogged objects. And so far I talked about how we balance load for read request. But is there a way we can also balance load for write request? So we use the property that we can send these write requests to any servers as long as we can remember which set of servers currently have the latest copy of the data. And we're taking advantages of these in-network coherence directories to track these server locations. And therefore, we're able to do a dynamic replica set, basically having a new replica set for each write request in order for us to balance write requests. And lastly, in order to ensure strong consistency, basically linearizability, so we designed a new version-based coherence protocol using the ability for these programmable switches to have a counter and also to do comparison on the data path. Okay, so now let me just quickly show you some of the actual load balancing benefit of using Pegasus. So here we measure the 99th percentile tail latency of the system, and we increase the workload skewness. And this is for read-only workload. So if we use a traditional approach like consistent hashing, it becomes ineffective when a workload becomes highly skewed because some of the servers becomes overloaded, and the request going to the server will suffer really high tail latency. So actually, the tail latency in those cases is more than 60 times the median. And because we have this queue built up, more than 40% of requests actually dropped. On the other hand, Pegasus is able to maintain its low tail latency across the entire skewness levels. So actually, for even a Zipfin distribution, Zipfin parameter of 1.2, which is extreme skew, it can still maintain less than 10% increase versus a uniform workload. And we're able to get more than 30 times tail latency improvement over a traditional consistent hashing approach. So we also run a comparison system called netcache, which caches application data in the programmable switches. And we're able to get comparable performance compared to netcache, while we use much lower memory consumption on these programmable switches. We are able to only store metadata instead of application data. And now to highlight the actual really cool aspect of Pegasus, here I show the throughput of the system when we have different read-write ratio. So again, using consistent hashing, because of load imbalance, the throughput is, and this is running at very high skewness. So consistent hashing, the throughput is always pretty low. But when you look at net cache, so it's only have really high throughput when it's read heavy. As soon as there are some untrivial amount of writes, the throughput drops by more than 90%. But then when you look at the throughput of Pegasus, it's able to maintain its high throughput across different read-write ratios. Because we are able to, for write-intensive workload, we're able to rebalance the replica set on every write. And at these high write-intensive workload, we're able to achieve more than 9 times throughput improvement over net cache. So in conclusion, so today I tell you guys about how we use the innovative use of these programmable switches to improve load balancing of distributed storage systems. So the technique we use is to selectively replicate most popular objects in the system. And we built an in-network coherence directories in these programmable switches to manage these replicated objects. And using this co-design approach, we are able to get more than 9x the throughput improvement compared to traditional consistent hashing approach. And thank you for your time. I'm happy to take questions.
I was wondering about the, maybe you could explain the write load balancing, because I don't really understand it. I mean, traditionally, if you want to load balance writes, you shard your data across multiple servers to reduce the load on servers. But in this case, it seems like we're replicating the data, so it's actually going to increase the load. So how could you tell, how are you actually reducing how are you doing the write load balancing?
Yeah, that's a great question. So yes, imagine you replicate a object on all the servers, and then for a write request, you have to send the write to all of the servers. So we will actually increase the overall load of the system. But the key observation we have is that if we can know the read-write ratio of that particular object, if the object is actually write-intensive, we can actually reduce the size of the replica set. For example, if it is write-only, we only need to actually replicate on one server. And because we're able to, for each write request, we can send the write request to any of the servers, as long as we can remember where we send the latest write. And that's the job of the coherence directory, because it processes both the request and the reply, so it can know when to update the directory to reflect the latest write. So there are two mechanisms. First, for each object, we track the read-write ratio of that object, replicated object. And then for write-intensive objects, we can try a smaller replica set and also rebalance each time.
Is there a single coherence directory for the entire set of servers, or are you balancing between multiple different coherence directories and multiple different switches?
Yeah, that's a great question. So Pegasus is actually working both ways. So we work on a rack scale storage system first. So it is the top of rack switch that is managing. So that is have all the requests and replies to that rack go through. And we also do multiple racks, but mostly for fault tolerance reasons. So we do chain replication across different racks to tolerate rack or server failures. So we have the observation that once we have a load balanced rack, for load balancing across different racks, we can use more coarser grain load balancing techniques instead of using coherence directories.
Any other questions? How do you tolerate errors? So you must, go out of sync, especially when you try to identify these flows and most popular flows. How do you tolerate that error margin?
Okay, so you're asking, so what kind of errors are you trying to asking?
Well, I mean, obviously you are not going to be able to identify the most popular ones instantly,
right.
right? So
Yeah.
how do you deal with that?
So yes, so this is kind of an approximation. So we are not always going to identify what's the most popular unlogger objects, but empirically we show that so as long as we can identify the approximate most popular unlogger objects, we're able to provide good empirical results. So it's pretty resilient to some small amount of errors.
All right, let's thank the speaker again.